We have seen in the previous module that assembling the external force vector for our problem is easy because the forces, external forces, are all applied at the nodes. In fact, they are only applied at node 5. That means uh, the external forces are all 0 except at degree of freedom 9 when it's minus F1 and at degree of freedom 10 when it's F2. On the other hand, for the entire superstructure or entire system, these are the degrees of freedom that we need to solve for. These are all displacements in the x or y direction. So the first one is x, second one is y, and so on. And the final equation that we have to solve is this, with f given by what we have here, and u is are the degrees of freedom that we want to solve for, and k is of course the global stiffness matrix which we have just assembled. However, I also mentioned that this equation is impossible to solve because K is a singular matrix and cannot be inverted. So you cannot just invert K, multiply it with F and get U. That's not possible. The reason that is not possible is easy to understand. If you look at our structure, it has some boundary conditions specified. So 2 degrees of freedom, 1 and 2, are fixed to 0 here, and another degree of freedom. So I'm looking at the changed numbering. I should go back to this numbering. So 1 and 2 are specified here, and I think 6 is specified here to be 0. So u1, u2, and u6 are taken to be 0, and this actually prevents the rigid body motion of the structure. So this is a planar structure, so it has 3 rigid body motions possible, 2 translations along x and y respectively, and a rotation about the z-axis. So all these 3 are prevented by fixing these 3 degrees of freedom, namely 1, 2, and 6. However, we have not yet transferred that information to this system of equations. This system of equation does not know that these boundary conditions are there to prevent the rigid body modes. Why is this a problem? This is a problem because, to understand why this is a problem, what you need to do is maybe not look at the entire structure, but look at just a single element, and that too in its own coordinate system. So in the XL-YL coordinate system, let's again look at this element flanked by nodes 2 and 4, and we have already seen that its local stiffness matrix for this element is just this, and you can immediately also see that this is a singular matrix. The consequence of that is, now if I apply a rigid body displacement in the, let's say, XL direction, then this would be, let's say, delta, this would be delta as well, and if you put this as delta, this as delta, then you will see that this will lead to zero forces. The forces are going to be all zero. That means that this solution is possible. This is a possible solution to this particular equation. Similarly, when we give a rotation, then in the limit that the rotation is very small, this is almost equal to 0, this is almost equal to 0, and you have displacements in the y direction that are equal and opposite. Even in that case, when say rigid body rotation of with displacement components 0 minus delta 0 delta are applied, even in that case these forces are 0. So these are known as zero energy modes because these cost us no external work. Remember, external work is the force vector dotted with the displacement vector. So it costs us no external work, and therefore these solutions, if these modes exist, then your stiffness matrix is going to be singular. So in order to make the stiffness matrix non-singular, you have to somehow weed out the uh, zero energy modes that cost no energy for them to occur. So in order to do that, we have somehow got to convey the fact that actually u1 is equal to 0, u2 is equal to 0, and u6 is also equal to 0 in this problem. So these three degrees of freedom are equal to 0. Now, computationally, it is of course possible to remove these three equations from the system. And remember, our K was a 10 cross 10 matrix. We can remove these three degrees of freedom and convert it into a 7 cross 7 matrix. We can remove those same degrees of freedom from F, and we can then solve the 7 cross 7 matrix, which is expected to be non-singular. However, computationally, reducing the size of a matrix is a little inconvenient. So we want to keep the size of the matrix, the stiffness matrix, and the force vector, displacement vector the same, but at the same time convey the fact that 1, 2, and 6 are 0 or specified to some value. These are known displacements, so our solutions should finally come out such that these known displacements retain their values even after the solution. So one way of doing that is, this approach is called the penalty method. We will look at the mathematical basis of the penalty method later, but now let us look at how this works. So we replace the stiffness elements in the stiffness matrix K. We replace the stiffness elements in 1, 1, 2, 2, and 6, 6 by a large number, because these three degrees of freedom are specified to some value. And now we call this new modified stiffness matrix as K prime. Similarly, we modify the right hand side force vector. Force vector had all zeros, and then it had minus F1 and plus F2 in the 9th and 10th entries. We keep that as it is, except at 1, 2, and 6 we replace it by LU1, LU2, and LU6. What it does is easy to see. Let us look at what happens to the first equation. So the first equation is multiplied. It's a U here, which starts from U1, U2, goes up to U10. Then it is equal to this new force F prime, which is LU1 here, LU2, then zeros, then LU6, and finally F minus F1 and F2. So this is how the equation is. So the first equation will be multiplied, L will be multiplied by U1, and then K12 will be multiplied by U2, and on the right hand side you have LU1. So when you divide by L, so you will have, this is wrong, you won't have the L here. So U1 will lead to the required value of U1 minus K12 U2 and up to K110 U10 divided by L. But since L is a large number, we can expect this to be almost equal to 0, which means U1 will tend to its designated specified value as L becomes sufficiently large. Now, what this basically means is, and I want you to figure this out carefully, is that in this structure, what we are doing is, in order to impose this constraint, we are actually, here both the degrees of freedom are fixed. So in this, we are actually putting a spring here in both the directions, and the spring stiffness turns out to be L. So if you look at this spring as a separate element and then you assemble the stiffness matrix, now not with 7 elements but 2 additional elements um, of stiffness L, whose one degree of freedom, one node is completely fixed, so 2 degrees of freedom are fixed. It is, this L is not adding any more degrees of freedom to this system, so the size of your stiffness matrix remains the same. Similarly, this is not adding any more degrees of freedom to your system. This end is fixed, so this is also not adding any more degrees of freedom. And similarly here, you can use another spring of stiffness L, not adding any more degrees of freedom. And if these springs are stiff enough, it will prevent the motion of this node and this node in the y direction. This is what exactly we are doing physically, then taking into account the fact that L is much larger than the entries in the original stiffness matrix K. You can easily show that after assembling this new system, which now has three new elements but no new nodes, no new degrees of freedom, if you assemble it, then this is the new stiffness matrix that you will get under the assumption that L is much larger than K11, K22, and K66. So this is the penalty method of applying the stiffness, applying the displacement boundary conditions. This is a little, this looks simple, but it's not very easy to use because you don't have an idea of how large L is going to be, and that definitely depends on the size of your stiffness matrices. Remember, in this case, our case, the stiffness matrix elements are of the order of K, which is defined as AE by L naught, and therefore on these parameters the values of these things will depend, and depending on the value of K you will have to choose an L. So it's not really independent of the problem that you're that you are solving. You have to choose an L which is commensurate with the material properties that you have specified. It has to be larger than any of the entries in the stiffness matrix, and we really don't have an idea of how large. Also, there is an additional problem that we will encounter later. If you make L too large, so if you make L too small, then this expression that we have written, this hope that we have, is not really fulfilled if L is small. If L is too large, then we risk making this whole equation ill-conditioned, whole system ill-conditioned, and that we will see later why that happens. So if L is too large or too small, we have problems. We have to hit upon the correct size of L, and that often is a problem. So this is not a very preferred method, though physically this actually means adding these stiffnesses, along the degrees of freedom that are fixed. Okay, so the more accepted method, more common method of implementing this boundary condition can be understood by a simple problem. Let us say I have a 3 cross 3 system of equations which is like this, and somehow I know the value of y. So y equal to delta is a specified solution. It's a specified boundary condition for me. Okay, then what do I do in the most high school or junior school kind of way? What I will do is I will say, okay, now there are two equations, actually two unknowns, x and z. Y is not an unknown, so I'll take it on to the right hand side. So the first equation will become a1x plus c1z equal to f1 minus b1 into delta. Delta is the specified value of y. This third equation will become a3x plus c3z equal to f3 minus b3 delta. And if you want to retain a second equation, that would actually be an identity, y equal to delta. So if I write this now as a matrix set of equations, and I don't want to reduce the size of the system, then I write it as a10 c1 0 1 0 a30 c3 xyz equal to this whole thing. And this quantity and this quantity here is written as delta times b1 0 b3. And what is this vector? This vector is this particular column in your system of simultaneous equations. So the coefficients b1 and b3 come from the column which is known in form of the specified solution. The column which is known, which is y in this case, it's known in terms of the specified solution, and that's why we have this column here. So in a finite element system, so now if you solve this equation, then y would come out to be exactly delta. Y would come out to be exactly delta always. So we have specified, we have managed to change the system in such a way that y equal to delta solution is always obtained, and then the others are solved according to that. We have modified the system of equations so that y equal to delta is always satisfied, and that we can do for our big global stiffness matrix. So we can obtain k prime and f prime, which are the modified stiffness matrix and force vectors, in exactly an analogous way as we have shown here. So we do this in two steps. In the first step, what we do is, if say 1, 2 and 6 are specified, then we first set uh, these columns. Let us think about the case where not 1 to 6, but let's say I1, degree of freedom I1, degree of freedom I2 are specified, and they are specified to values delta I1 and delta I2. So suppose these two are specified. So in the I go to the I1th column and the I1th row, and then set the entire row and entire column equal to 0 except the diagonal element, which I set as 1. I do the same to I2 and set it all, the column to 0, the row to 0 as well, except the diagonal element, which I keep as 1. So this is I2. This is what I had done here. I had set this whole row as 0. I had set this whole row as 0 and kept the diagonal element equal to 1. That's what I did here for I1, I did for I2, and I can keep doing if there are n degrees of freedom that are specified. So this is the modification that I need to do on the left hand side. On the right hand side, before I do this, I'll have to take this column, and multiply it by the specified displacement of this column, or the specified degree of freedom corresponding to this I1 degree of freedom, and that is delta I1. I'll have to multiply it with delta I1 and transpose it to this side. Similarly, I'll have to multiply this column. Typically, this is done before this operation is done on the stiffness matrix. Multiply this column by delta I2, which is the specified value for I2, and then transpose it there, and have to continue doing this for all the n, small n number of degrees of freedom that are specified. And this will give me a new force vector, which I called F double prime. What I'm doing here is I'm doing this step. This is the specified value of y multiplied by the column corresponding to y. So B2 is also there. At this stage, B2 is also there. I have taken this column, multiplied it with delta, and then transpose it to the right hand side. And this is what I have done in this particular case. Now, in the last step, what I'll have to do, this B2, I'll have to set it to 0. Then I have exactly this kind of a set of equations for the large system. So from this F double prime, I will have to get rid of the degrees of freedom that are specified, and they are specified as delta I1, delta I2, etc. And I replace these things with delta I1, delta I2, all the way up to delta IN if I1, I2, IN are the specified degrees of freedom. So this process you need to understand very carefully. Both the assembly process and the application of boundary conditions in this way are essential parts of a finite element program and need to be coded very, very efficiently. So in the end, the general structure of a finite element program looks like this. So first you read in the information that the user supplies, which is, as I have said, nodal coordinates, element connectivities, which element is connected to which node, force and displacement boundary conditions, and the material properties of each and every element. This is typically the essential data that your user has to supply. Then you have to form a destination array depending on how many nodes, how many degrees of freedom per node you have. Then there's a loop over each element. Uh, in that loop, first you form the local stiffness matrix. For the truss, we have done it. Then form the local RHS vector. For the truss, this was a trivial step. There was no RHS vector for an element, but we assembled it directly from the nodal forces. But in other cases, as we'll see later, you may have elemental RHS vector, which you will then have to assemble into the global stiffness. In this case, we did not have to do. So once you form this, you assemble it immediately into its right position in the global stiffness and the global RHS vector, and you do that using the destination array that you have formed. Then this loop ends and it continues over all elements. After this is done, you get a stiffness matrix which is singular. So you have to incorporate boundary conditions into the stiffness to make it non-singular. You also have to modify the right hand side to get your K prime U equal to F prime equation. Then finally you solve this equation. This is no longer singular, so you can solve it, and that's the end of the story. Now we have done all these steps for the truss. We explained all these procedures, and as I said, this step and this step are extremely important. They are extremely general. They work exactly the same way for the truss as they will work for more complex elements that we will deal with later. And these have to be understood very, very carefully. In the next class, in next week, we will concentrate on this part where we will look at what methods we have at our disposal to solve this large set of simultaneous equations. We will end this here.